All right. Hello, everyone. Thanks for joining us. We are very happy to have today Dylan Langharst from Kent State University, who is going to talk about the Gaussian Brunn-Minkowski theory for convex bodies. Please, Dylan.
All right. Thank you for having me. So first, I should tell you what a convex body is, and then what the Brunn-Minkowski theory is. So I remind you that K, can I zoom in? Is that possible? It is, but now right, there we go. I remind you that a set K is convex if for any 2 points in the set I take. So here's an unbounded one. So this is X, this is Y. If I connect them with a line segment and say I parameterize this line segment as so, where lambda is in 0, 1, this entire line segment must be inside the set. And we usually deal with convex bodies, which simply means it's convex and also compact. And for pedagogical reasons, we'll also assume non-empty interior. So here's an example of one I stole from my advisor, just kind of your standard n-gons are kind of the classical convex bodies. And in some sense, the study of convex geometry is just trying to generalize these classical n-gons. And here's another one. So not just n-gons, but also spheres and ellipsoids. So for notation, you can zoom in. There we go. So for notation, I'm going to denote kind of volume subscript n of k to be the volume of some Borel subset of Rn. So it doesn't have to be a convex body. And by volume, I mean Lebesgue measure. And maybe for simplicity, I might just use absolute value signs. Now, given two Borel sets, one can take their Minkowski sum, which is merely just kind of this pointwise vector sum. And it turns out the set of convex bodies is closed under Minkowski sum. But if I zoom in, I can't scroll. Very interesting. So as an example, if I have two line segments and I add them, I get a square. So technically, in this example, line segments aren't convex bodies because in R2, they don't have a non-empty interior in some sense. And now a less trivial example is if I have a square and I want to add a triangle. So essentially, you see if I take a point, 2 points in their interior and I add them, they don't kind of contribute. So this shows that it suffices to really take your entire convex body and only add it of the second one and only add it to the first one to make your Minkowski sum of the convex bodies. And so now we're working towards kind of the classical example, maybe the original reason why they studied this. So if I have a square and I add a circle, I'm going to zoom in really far. Please work. Thank you. I kind of get this curvy square. And now a natural question is, what is the volume of what I added? So let me do a harder picture to really emphasize it. So I see this dilated guy where I took this convex body K and I added a ball. It contains the original convex body. You can see it here in the blue. And now the question is, how do I calculate the area of the kind of curvy part? Well, say the radius of the ball I added, let's say it's t. Then I see I have a whole bunch of these rectangles, and I know the width of them must be t because it's the same as the radius of the ball. And the height is the boundary of your original convex body K. I mean, and restricted to this rectangle. And now at the corners, you have kind of this error, these curvy parts here. But I want you to notice that the sum of the errors is the Euclidean ball. So it's highlighted in the picture that if I kind of take all these errors, I just get the Euclidean ball back. Well, this dilated Euclidean ball. So thus we conclude that for this picture, the volume of K plus the dilated Euclidean ball is the volume of K, which we saw on the inside, plus the volume, the sum of these rectangles, which is this, plus some error. And we know that it's, the area of the Euclidean ball. And since the area behaves quadratically, it's going to be t squared. So now I can solve for the volume of the boundary of K by simply just taking the derivative. So for notation, B2n will henceforth denote the Euclidean ball. And I also remind you that volume is n homogeneous. So if I have some constant lambda, it'll pop out to the power n. So if I kind of combine this idea of homogeneity and taking Minkowski sums, we get what's called the Steiner polynomial. So it turns out if I have convex bodies and I sum them up with some coefficients, so say I have K1 up to Kr convex bodies, and I have coefficients lambda 1 up to lambda r, and I sum them up and I take their volume, I can expand this as a homogeneous polynomial, and we call the coefficients of this homogeneous polynomial the mixed volumes of the convex bodies, and you sum over all possible combinations. So here are some properties of mixed volume. If I take all of them to be the same set, you just get the volume of K. Please scroll. And it's also symmetric in its arguments. So do I write explicitly the example? Please scroll. I do not. So what I mean by this is that if I have, let's say we're in n equals 3, and if I have K, L, and M, well, that's the same as L, K, and M. I can switch them. And also it's multilinear. So in each argument, so if I have coefficients and two bodies, I can distribute. So here it's Minkowski sum. And here it's sum of two vectors. Okay. So now I've learned I have to zoom out. And finally, it inherits the translation invariance of volume. So if I add any vector to a convex body, I get the same to any of the convex bodies in the arguments. And also, finally, it's monotonic with respect to set inclusion. So if I fix all the other convex bodies, and then I say the first one, let's call it K, is inside some set L, then whenever I switch K with L, it only gets bigger. But I'll be honest with you, we don't need this. This notation looks kind of hard to follow. So in our setting, we're only going to be dealing with kind of bodies that appear multiple times. So let's say here I have n total bodies, but this last convex body K appears n minus m times. So I'm going to simplify the notation and use this. So I have K1 up to Km, and then this last one appears n minus m times. And moreover, we're going to be concerned with whenever one convex body appears n minus 1 times, and another convex body appears once. And for this special case, I'll just use VKL. Now I want to emphasize that with this notation, it's not symmetric in the arguments because K appears n minus 1 times and L only once. So if I switch them, now L would appear n minus 1 times. So if you see this, it's not symmetric in the arguments. So as an example, what does it look like if I, take K, dilate it with a ball, and I then take the Steiner polynomial? Well, it looks like this. And, there's something special about the second body being the Euclidean ball. So it kind of looks like the binomial theorem. So now we recall on the previous slide, we only showed it in dimension 2, but the argument's essentially the same in higher dimensions, that the volume of the boundary of a convex body is this derivative. But if I insert the Steiner polynomial, so I get these are the higher order terms, but they'll go away in the limit as t goes to 0. I just get that the volume of the boundary of K is just a multiple of the mixed volume of K with the unit ball. Now, given a convex body, it's uniquely defined by its support function. So what you do is you have your vector x, and you take the largest projection of x onto your convex body K. So I have a picture to show. So say I have my vectors E1, and then where E1 is just the standard 1, 0. And then what I do is I take the hyperplane through the origin orthogonal to E1, but then I move it in the direction of E1 until it just touches the boundary of K. And then the support function of K evaluated at E1 will be the distance I had to move it, as shown here. So that is HK of E1. I wish there was a way to get rid of this boundaries. It takes up a lot of this screen space. So now using the support function, I obtain a nice formula for the mixed volume. So just going back to the polynomial definition, I see a mixed volume, which is be the derivative, which is written here. So essentially the 1 over n is kind of just from these combinatorial coefficients from the binomial expansion above. And so we get 1 over n, integral over the sphere, and I have the support function of the first body, and then I have this surface area measure of the second body. Now we'll describe explicitly what that is on the next slide. But I remark that if I plug in this formula to our results for the volume of the boundary of K, I just get that the volume of the boundary of K is just the integral over the sphere with respect to the surface area measure of K. So in fact, this name surface area measure is apt. So here it is. Here's the explicit definition. I have the text up, but you know what? Don't read the text. So this is what we're going to do. We're going to make a polytope. If I can draw. And so here's my polytope. Now let's say I label the faces. So this face is outer unit normal U1, U2, U3, U4, 5, U6, U7, and U8. And now if I label the faces Fi, then clearly the volume, so I'm going to call this P for polytope. The volume of the boundary of the polytope is just the sum from I equals 1 to 8 of the volume of the faces. So Fi. So how can I make this a measure? Well, it's simple. On the sphere, I take all these outer unit normals, and we call the map, which sends a vector on the boundary of a convex body to its outer unit normal, the Gauss map. So I use the Gauss map. So here it's NP. And it sends all the vectors on the boundary to their outer unit normals. So it collapses each face to these single vectors. And now at each outer unit normal, I'm going to put a point mass, the Dirac measure. So this is delta UI1, delta U2, and delta U3, and you get the idea. And so now my measure, which I'll put up here, DSP of U, is just the sum over I equals 1 to 8 in this example of the volume of these faces times these point mass UIs. And so now it turns out that polytopes are dense in the set of convex bodies with respect to the Hausdorff metric, blah, blah, blah. And it also turns out that discrete measures are dense in the set of measures. So via approximation, you can construct the surface area measure of any convex body in this way. So explicitly, you'd have your some Borel subset of the sphere, and then you map it backwards through the Gauss map to put it on the boundary, so up here. So E is my Borel subset of the sphere. I do the pushback of the Gauss map to put it on the boundary of your convex body K, and you integrate with respect to the usual Hausdorff measure. So this approximation type argument will go to this guy. So now that you've seen the introductory, what is convex bodies, what is the Brunn-Minkowski theory? Well, the Brunn-Minkowski inequality tells you that if I take the Minkowski sum of two convex bodies K and L, and I raise it to the 1 over n, I'm going to really zoom in and emphasize this, you get this inequality. So that the sum to the 1 over n is greater than or equal to the volume of K to the 1 over n plus the volume of L to the 1 over n. And Minkowski's first inequality talks about the mixed volumes. It says the mixed volume of K with L raised to the n is greater than or equal to the mixed volume, or to the volume of L times the volume of K to the n minus 1. So see here that the exponent here matches the number of times K and L appear here. So now using these formulae, we get an isoparametric inequality, the famed one that was discovered by the Greeks. So we know that the volume of the boundary of K is a multiple of the mixed volume. I use Minkowski's first inequality to get this. But now this constant n, I know I can replace with the volume of the unit sphere, because we know that the volume of, well, it's zoomed in, but that's okay. the volume of the unit sphere is just n times the volume of B2n. Usually at this step, you write it like this. You divide through by the volume of K, and you raise everything to the n, let's say. Let's do it like that. So this is this volume of K to the n minus 1, greater than or equal to volume of the sphere, unit sphere, over the volume of B2n to the n. So kind of this ratio is minimized by the unit ball. And another way to write this is if you replace K with the Euclidean ball of the same volume, then that tells you among all convex bodies with the same volume, actually all compact Borel sets closed under Minkowski sum, that the ball has the minimal surface area. Okay, so I want to kind of write these inequalities in a different way. So using the homogeneity of volume, I can replace K with 1 minus lambda times K, L with lambda times L, where lambda is in 0, 1. And now the Brunn-Minkowski inequality is written as such. But you might recognize that this is just saying that volume raised to the 1 over n is a concave function on the class of convex bodies. Moreover, if I raise both sides to the n and then use Jensen's inequality, I get that volume is what's called log concave. And what's absolutely amazing is it turns out, so what do? We started here, let's zoom out. At this version of Brunn-Minkowski, we went to here using homogeneity, and then we went to this version using Jensen's. And what's absolutely amazing is that the loop actually completes and that they're all equivalent. Now, using that the concavity, we can prove to you Minkowski's first inequality. We're going to do it right now. So it's just simply define a function to be the left-hand side of Brunn-Minkowski minus the right-hand side. So this function from the Brunn-Minkowski inequality is greater than or equal to 0, but we see 0 at 0. So therefore, the derivative at 0 must be increasing, or non-negative. So if you just take the derivative and use the definition of mixed volume as a derivative, you get Minkowski's first inequality. However, we also know that this function is concave. So therefore, its second derivative is less than 0. So if you write it out, you get Minkowski's second inequality, which is this, that the mixed volume of K with L squared is greater than or equal to the volume of K times VKLL. So here I'm introducing one notation. So VKLM is the mixed volume of n minus 2 copies of K, 1 copy of L and 1 copy of M. And for now on, we're just only going to be dealing with mixed volumes if it has 2 or 3 bodies. Now, I'm going to not show the proof of this, but using Minkowski's second inequality, you can get Minkowski's quadratic inequality. So for some reason, psychologically for me, if I have 2 bodies, I call them K and L, but if I have 3 bodies, I call them A, B, C. So Minkowski's quadratic inequality states that the mixed volume of n minus 2 copies of A with 1 copy of B and 1 copy of C. And I want to remark that in this instance, it is symmetric in the last 2 arguments because B and C are each appearing once. Is greater than or equal to the mixed volume of n minus 2 copies of A and 2 copies of B times the mixed volume of n minus 2 copies of A and 2 copies of C. Now, if I take the difference, you can write it as this. Now, Minkowski's quadratic inequality is just a special case of what's known as the Alexandrov-Fenchel inequality. So for n bodies, but again, in our scenario, we don't care about the n bodies. So moving on. Now, consider the function of 2 variables. Volume of A plus SB plus TC, all to the 1 over n. As a function of 2 variables, this is concave over R2, and particularly at the origin. So therefore, its Hessian, if it will scroll, the determinant of its Hessian is non-negative, and you obtain this inequality. And so if I insert what these derivatives are, if it will scroll, please, I get this. This is a reverse to the quadratic inequality. So it's an upper bound. So remember, the quadratic inequality said this was greater than 0. So I get an upper bound. Please scroll, I think. Okay, so now that you've seen kind of the foundation of the Brunn-Minkowski theory, we're going to generalize to measures with density. So I have it written here, and it's very technical. You know, we say the set lambda will be the set of all locally finite regular Borel measures mu, whose radon Nicodemus derivative, blah, blah, blah. All that means is I can take my measure mu, and it has a density with respect to Lebesgue, and that density is locally integrable. But, you know, let's just think continuous. We don't have to get fancy here. So many people have considered, but kind of more recently it's been taken off due to Lifshitz, kind of measure theoretic surface area measure. So we take that definition we saw before for surface area of a convex body. And now we take our Borel measure mu. So mu in lambda means mu is a Borel measure, that has density with respect to Lebesgue. And let's call this density phi. So then we can just take the density and just shove it into the definition of surface area for the classical definition. And that's how you get measured theoretic surface area. So I need to tell you more properties about how we can classify a convex body based off of its behavior of its boundary. So we say K is strictly convex if its boundary does not contain a line segment. And what's absolutely amazing is that when this happens, the Gauss map, which remember associates a vector on the boundary of a convex body with its outer unit normal, is an injection between the boundary of K and the unit sphere, as long as you delete a set of measure 0 where the Gauss map isn't well defined. So maybe some vectors that have multiple outer unit normals, like think corners. Come on, please scroll. Okay, so I just wanted to remind you, so this went much more smoothly when I didn't have to scroll with my fingers. I wanted to remind you that the formula for the measure theoretic surface area. And what's interesting is in the classical volume case, if the support function of a convex body is of class C2, so twice differentiable, then the surface area measure has density with respect to the spherical Lebesgue measure. And we call that density the curvature function. Please. And this holds true with this measure theoretic surface area measure in the following way. If K is of class C2+, i.e. K is strictly convex, has positive curvature in the differential geometry sense, which we'll push under the rug, and its support function is twice differentiable, then the measure theoretic surface area measure also has density. And this is what it is. Now, that sounds like a lot of requirements in our convex bodies, but believe it or not, you can actually uniformly approximate any convex body with a sequence of convex bodies that are C2+. So actually in application, it's okay. So essentially all this is saying it's okay to treat the Gauss map as a function that will have an inverse because we can always approximate uniformly. Always is a strong word, you know. You always say always until you actually try. So we talked a lot about all these inequalities, you know, Brunn-Minkowski and Minkowski's first inequality and second inequality. So kind of the generalization of that is F concavity. So I have some Borel measure with density mu. I'm just going to say that there exists a class of compact Borel subsets, which we'll call fancy C, where Minkowski sum takes sense, and all of that class is in the support of mu. Then we say mu is F concave, where F is continuous and invertible, such that if I take any two elements in this class, fancy C, and I take the mu measure of their Minkowski sum, it's greater than or equal to F inverse of the convex combination of these outputs. So when F is x to the s greater than 0, this can be written as so. So this to make it seem more familiar. And we say mu is S concave. So we saw earlier that the volume was log concave. And in the limit as S goes to 0 of S concavity, we obtain the case of log concavity here. Come on. All right, so now we introduced this measure theoretic surface area measure. So now the next question is, have people, what's the historical context for this? So now here we finally get to introduce, I don't know, the hero of our story. So the Gaussian measure, or the standard distribution Rn, which is, I remind you, is given as so. Now for a compact Borel set K, we kind of take this it's kind of like the mixed volume we saw before. We take the lim inf of essentially the derivative. Like you take k and you perturb it by a ball, you take the difference quotient. And we're going to denote it by gamma n plus of the boundary of k. So you can check with a set inclusion that it reduces to this nice, pretty formula. It's just integrating the Gaussian measure over the boundary of k. I also want to remark that, so if say you have a function that goes from the interval 0, 1 to the interval 0, 1. So you know the function is bounded by 1, but that doesn't mean its derivative is bounded by 1. So even though the Gaussian measure is a probability measure on Rn, this gamma n plus is not. You know, this, in fact, in a paper by Keith Ball, he was able to construct a polytope where gamma n plus of the boundary of the polytope was of the order log n. So, you know, this doesn't have to be 1. That's what I'm trying to get at. You know, the derivative can be unbounded. Just look at something like this. So Keith Ball showed, and then Fedya Nezra showed, it was asymptotically shot, that the Gaussian measure plus of the boundary of k is bounded above by 4n to the 1 over 4. Now, to kind of connect this historical story with what we're talking about now, we simply see that the measure, so if I have some Borel measure mu, and I construct the measure theoretic surface area measure of a convex body k, and then I measure the whole sphere, that's the same as mu plus of the boundary of k. So we have to connect the two ideas. And while we're talking about the Gaussian measure, let me mention that the Gaussian measure is log concave over the compact Borel subsets of Rn. And it's also Ehrhart concave. So if I have the function phi of x, which is the Gaussian measure of the interval -infinity to x, then the Gaussian measure is phi inverse concave. And this is called the Ehrhart inequality. So in the F concave equation we saw before, I can let F be phi inverse. And very recently, it was shown the Gaussian measure is 1 over n concave over the set of symmetric convex bodies. And this was shown in a series of papers by Gardner and Savovich, Plesnikov and Lifshitz, Eskenazis and Mushitz. All right, so now we've introduced our measure theoretic surface area. We saw the generalization of concavity. Let's finally generalize mixed volume. So here's a definition, which again, you know, has appeared historically, but we're following kind of a standard notation, kind of hammered in by Lifshitz, Millman, and Rodham. So I have some measure mu, and I have some set where Minkowski sum makes sense. Then the mixed measure of k and L is simply the lim inf we saw in the previous slide. But now L doesn't have to be P2N. And we obtain this lemma, which is Lifshitz integral equation. It just simply says if k and L are convex bodies, then the lim sup exists. The lim sup equals the lim inf, so the limit exists, and the limit is precisely this formula. Now I want to mention that in the volume case, we're missing 1 over n. Remember, in the formula for mixed volume, there was a 1 over n here. So we're missing the 1 over n here. So sometimes when you're looking at these inequalities and you have to figure out what's the equivalent inequalities for measures, 1 over n's need to appear or disappear to compensate for this discrepancy in the definition. Okay, so I keep the definition up. Please scroll. Now, before we saw the mixed volume of n-1 copies of k with k was the volume of k, but that's actually not true for measures in general. Now, I want you to notice that the mixed measure of tk with k is simply the derivative of mu of tk. So consequently, using the fundamental theorem of calculus, I can integrate. So I get mu of k, it's just the integral from 0 to 1 of mu of tk k dt. And if I insert, that becomes precisely this. And to compare this to a well-known formula for the volume of a convex body, which is given as so. And if you wanted to prove this formula, well, you just take a polytope, break it into cones, like this. That last one's good. And then the height here is hk of ui. So if the polytope is k, this outer unit normal here is ui. This right here is the volume of fi. And the whole volume of this cone is 1 over n. height times base times what's already written. So that's how you prove this formula via polytope approximation. So, and notice if this is volume, the t pops out to the tn minus 1, and then you can integrate, and this reduces to this. So this is why you don't want to introduce a 1 over n up here, because the 1 over n will appear for free after you insert that the measures will take. Now, if mu is alpha homogeneous, which I remind you, that means if I put a t here, it pops out to t to the alpha here. One obtains that this mixed measure is alpha minus 1 homogeneous in the first variable, and furthermore, that mu of kk is alpha mu of k. So there's our missing, again, 1 over n. If I bring it over here, you get the 1 over n. So it all reduces back down. All right, so everything I told you up to now was the history. We did the volume stuff, and then we did the measure stuff. I can very finally tell you what something new. So me with my advisors, Artem Savovich and Matthew Ferdolisi, and their colleague Mokshay Madhuman, we were just like, what if we just take one more derivative? So we defined the mixed measure of m minus 2 copies of A, 1 copy of B, and 1 copy of C, to be this second mixed derivative of mu of A plus SB plus TC at 0, 0. Now you can define anything you want, but the hard part is then making it useful. So our first, I should mention that there exists an integral formula for the mixed volume of n minus 2 copies of A, 1 copy of B, 1 copy of C. So there exist these mixed surface area measures. So our first main result is we were able to obtain a formula for the mixed measure of n minus 2 copies of A, 1 copy of B, 1 copy of C. So here I made a stray mark. So this is it. And essentially it's just the product rule. So here we took the derivative of the volume and we got the next surface area measure. And here we had to take the derivative of the density. So here mu is a measure with density phi. So it looks kind of complicated. Let's just see. Oh, I should mention that, look at this guy. Look way back here. If I came up to you on the street and I showed you this formula and I pinky promised you that this was symmetric in the variables B and C, would you believe me? No way, I wouldn't believe me. But remember where this came from. This came from a second mixed derivative. So from the Schwartz lemma from multivariable calculus, it's true. This actually is symmetric in the second and third variable, which is it's amazing. So let's see what it looks like for the Gaussian measure. You get this nice pretty thing. You know, the gradient of the density, I use chain rule. You get this extra interplay between the convex bodies, which in practice is really hard to account for. And what's even interesting is that this integral might be bigger in value than this integral. So this mixed measure of n minus 2 copies of A, 1 copy of B, and 1 copy of C could be negative. So here's just an example of how the behavior here is pretty weird compared to the volume case. Take some vector kz on the sphere and construct a line segment that connects minus kz to kz. Then the mixed volume of A with this line segment twice is 0. But if I input this B up here, I get this guy, which is not necessarily 0. Oh, I should have mentioned a little bit back here that in order to take the calculation, we had to assume A was C2 plus, so we could treat the inverse Gauss map as a function. But you can actually drop that requirement in some sense, because if you would you can approximate any convex body by C2 plus bodies, and you can show that the limits will exist, but we're not quite sure what the limit will go to. Like, what's the formula for the resultant guy? So we just leave it as, here's what it is for C2 plus body. But when A is C2 plus, B and C can be anything, any convex body. Please scroll, please scroll. I went too far. No, yes, okay. So now let me show you Minkowski's first and second inequalities for F concave measures. So Lifshitz showed the case of the first inequality. So if mu is f concave, by the way, all these definitions up until now for the mixed measure of A, B, C, we didn't assume any concavity. It was just a definition. Now we're assuming concavity. So Lipschitz showed if mu is f concave, then you get this guy. And we were able to show, and believe it or not, this actually does reduce to the classical one, i.e. this is I remind you, this is the equivalent of KL to the n. It's greater than or equal to, oh no, this is, yes, this is right, volume of K, n minus 1 volume. And then we were able to take one more derivative now that we have the definition, and this is what we get. And so remember, this is the analog. I think I have it up actually. We'll get to it. I also want to kind of point out something that's pretty and cute. If mu is alpha homogeneous and 1 over alpha concave, this guy right here reduces down to this nice, pretty formula. And so here again is 1 over n that we were missing from the definition. It just appears on its own naturally. And this was first shown by Millman and Roda. So you can clearly see that this is the volume case, essentially. So here are the volume inequalities again. So using Brunn-Minkowski, you prove Minkowski's first inequality and then Minkowski's second inequality by taking 1 and then 2 derivatives. And so here, using f concavity of some measure, if you take 1 derivative, you get this, which was shown by Lipschitz. And if you take 2 derivatives, you get this. And now I also remind you that there was Minkowski's quadratic inequality, and then there was this reverse one. I wrote it in a different way by multiplying through by a minus sign. And now you can see that the reverse is weaker than the original, because the original then tells you that this is less than 0. So in some sense, the original is telling you something about the reverse. And so our next big theorem is we were able to prove the reverse Minkowski's quadratic inequality. And here it is. It's just a nasty, awful thing. But we were able to do it, and that's what matters, is that some inequality exists that can be used, but I wouldn't expect anyone to memorize this or even read it, unless they need it. So I kind of told you about all these classical inequalities, and then I told you about our generalizations of these classical inequalities. But now I would like to tell you about inequality that's still cutting edge, even in the volume case. And then I'll be able to show the progress we made in a measure theoretic version. But I need to introduce spaces of convex bodies. So fancy K will denote the space of all convex bodies. Fancy K subscript 0 will be those convex bodies containing the origin. And fancy K subscript sim will be symmetric convex bodies. And of course, you have the obvious set inclusion. Every symmetric convex body contains the origin, and every convex body that contains the origin is a convex body. And it turns out each of these sets is closed under Minkowski sum. Okay, so now I need to tell you what a zonotope is. So if I have 2 vectors, alpha I and beta I, and I construct the line interval connecting them, and I'm going to use an interval, like a notation, interval notation. And then maybe I have some coefficients, Ci. And then I sum up all of these scaled line segments. So we say Z is a zonotope if it's written as the Minkowski sum of line segments. And then of course, in the limit, as the number of line segments goes to infinity, you get a zonoid. So a zonoid is the limit of a Minkowski sum of line segments. And fancy Z will denote the space of zonoids. Please go, thank you. Fancy P will denote the space of polytopes. And now here's an interesting remark. Let's C be a class of convex bodies closed under affine transformations. And let's say K is equivalent to L if K is equal to TL for some affine transformation T. Then this class C under this equivalence relation is compact. And why is this important? Well, if you can create something that's affine invariant, then as a function of convex bodies, then it should have a maximum and a minimum. Okay, so now we get to, which is slowly being called Bezout. It's kind of like a reverse Alexandre-Fenchel, but we're kind of calling it these days a Bezout inequality for reasons that connect to algebraic geometry. So let's say we have some class C of convex bodies, and we're going to fix some convex body in that class. Then what is the constant BCA? So it depends on your class and your fixed convex body, such that for every other two bodies, B and C in the class, the volume of A times the mixed volume of A, B, C, where again, this means n minus 2 copies of A, 1 of B, 1 of C, is less than or equal to this constant times the mixed volume of A with B, where again, this means n minus 1 copy of A, 1 copy of B, and mixed volume of A with C. And we know a maximum exists because if we consider this function as a function in two variables for fixed A, it's affine invariant, as in the variables B and C. So we know a maximum exists. And it was shown by Zhao that over the set of all convex bodies, so here fancy C is fancy K, then for every convex body A, the constant is less than or equal to n. That is the volume of A times the mixed volume of A, B, C is less than or equal to n mixed volume of AB times the mixed volume of A, C. And here's a conjecture that for every zonoid A, this constant is less than or equal to n over n minus 1, written for you explicitly here in the volume case. So now let me tell you about the progress that's been made in the volume case. So here's the conjecture again. I have it up. So it's true in dimension 2 and dimension 3. So this is shown in a series of papers by Surpanov and Savovich and Fredolisi, Madaman, Mayer, and Savovich. So as you can see, this has been this Bezout type inequality has been very close to my advisor's hearts. They've been working on it for a very long time, picking away at it. And so it was shown by Hugh and Schneider that if A happens to be the Euclidean ball, then it's true, i.e. this constant Bzn B2n is less than or equal to n over n minus 1. And Archstein, Avedon, Florentine, and Strober were able to extend this. So A is still B2n, B is any zonoid, but now C can be any convex body. But actually, they did better. They were able to improve the constant. They have a weird kappa n minus 2. So maybe I don't know if I wrote it before. Oh, I wrote it now for you right here. Kappa n is the volume of B2n. So they're able to introduce this constant here. And this is sharper because this constant is less than 1. So what they have shown is that like Bzn, to use this notation I've introduced, is less than or equal to n over n minus 1. Kappa n over kappa n squared n, which is less than or equal to n over n minus 1. So it's sharp. And so we were able to replicate the result from Archstein, Avedon et al. So rotationally invariant log concave measures. So now in the volume case, volume, is homogeneous in each variable. So let me go back here. If I replace, so remember, this is a typo. These A's should be B2Ns here and here. So if I replace B2N with R B2N, the R's will pop out everywhere and they'll cancel. But here, for a rotationally invariant log concave measure, it's not homogeneous. So we have to not check it on just R equals 1, but for all R. And we get a constant here that depends on R. However, this constant, so I cheated a bit. Psychologically, for me, it was easier to move all of these constants to the other side. So now, yes. So now this ratio flipped here. So the n over n minus 1 disappears actually due to the discrepancy in definition of mixed measures, meaning that the dream, so in the volume case, dream is that this constant is 1 because the n over n minus 1 again disappears due to the discrepancy in these mixed measures. So we were able to get a constant better than 1. So this constant, which depends on the radius of the ball, is always greater than or equal to 1. And we went greater than and not less than because I moved it to the other side of the inequality. However, you can't do better than this constant because in the limit as r goes to 0, you get exactly. So we're able to improve the results to the rotationally invariant while concave case. Now, what if you know beforehand that your measure mu, so I'm going to erase all these arrows so this is readable. What if you know beforehand that your measure mu is the Gaussian measure and that the radius of your Euclidean ball is 1? Well, then you can do even better than this theorem. So I'm going to read this one out explicitly. So fix some dimension greater than or equal to 2 and have some zonoid C and any convex body C containing the origin. Then the mixed Gaussian measure of B2n with the zonoid times B2n with the convex body is greater than or equal to this constant times the Gaussian measure of B2n times the mixed Gaussian measure of B2n with Z with C. And furthermore, this constant here is sharper than this. And that's all I have. We have some other results, but we're actually still, working away to get those in the best form. So I will end it now. Thank you very much for listening.
Thank you, Dylan. Are there any questions? All right. If this is not the case.
Dylan, okay. I have a question about the constants here.
Yes.
Do you have any intuition whether they're actually optimal?
You mean so in the case where A is RB2N or in the general case for all zonoids?
No. When it's RB2N or even for the Gaussian, the latter result.
Yes, so here we know this one is optimal because as a function in R, it's a maximum is attained to R equals 0. And so like, I don't know, DDR of A mu of R is decreasing. So at R equals 0, it's so you can't, if you claim you do better, well, then I can find you a convex body that's, smaller and the constant won't be better. So this right here is optimal because of this asymptotic behavior. And in the Gaussian case, if there was equality here, then there would be equality in Jensen's inequality applied to a specific integral, which I forget. So that's how we got this, is we applied Jensen's to some Gaussian type integral, like some 0 up to, like n or some function of n, like f of n, and like Rn minus 1 e minus r squared over 2 dr. And we apply Jensen's to bring this e out here. And so if there's equality, then that would apply equality in Jensen's, which can never happen. So this is optimal. This is also sharp because of the Jensen.
Okay.
However, if we want to replace B2n with some other arbitrary zonoids, we think the constant should get worse. So we only get these sharper constants because we know B2n is fixed. So for all zonoids, the constant shouldn't be as good. So these should go away, actually, we think, for all zonoids.
Have you tried with the cube or not?
We started, and then that's hard to compute.
Okay.
Yeah. Thank you.
All right. Are there any other questions? Okay. If this is not the case, thank you again, Dylan. And
Thank you.
we hope to see you all next time.
Thank you.